So I'll be talking about actually buoyancy effects in some astrophysical systems called galaxy clusters. And actually it's the physical effect is quite profound. It changed the, I mean, if we include the effects that I'm going to talk about, the nature of buoyant response in such dilute astrophysical plasma changes fundamentally from normal convection. So I'll talk about two instabilities which are very intimately related to normal convective instability, but are essentially driven by thermal conduction rather than the adiabatic response of a displaced blob. These are, WKB, very simple linear instabilities. And I'll actually talk about applications. So since in terms of the technique, it's actually very, very simple compared to the sophisticated talks that you heard in the morning, and but it's an application which is quite different. So, everyone knows about normal convective instability, that if you take, if you have a stably stratified fluid, and if you displace a blob from its mean position, it experiences a restoring force which pushes it back to its original position. And, you can do linear stability analysis and show that for normal flow like this, for a normal stably stratified flow, this arrangement is convectively stable if the background's entropy increases with height, or the density decreases with height. So, usually in oceans, this is written only in terms of rho, but in astrophysics, for example, in the sun, we sort of talk about entropy. It's quite interesting that different fields have their own ways of defining things, essentially the same things. So here is sort of a toy calculation, and I'm not going to, repeat it because it's been repeated quite a lot of times, I'm sure. But the point to remember is that when you displace this blob, you assume that it doesn't exchange heat with its surroundings. So P over rho to the gamma for this blob is the same, okay? And then you go to a new height and equate the pressures of the displaced blob and the background, and see at the same pressure whether this displaced blob is heavier or lighter than its surroundings. If it is heavier, then it will come back, and there's a restoring force, and it's a stable situation. And this is the Brunt-Weisseler frequency square, which we have heard about a lot. Now, what I'm going to talk about is that this assumption of adiabaticity of this blob is not valid in astrophysics, in a lot of astrophysical systems. I cannot say that, for all systems, because, for example, in the convection zone of the sun, it's perfectly valid. But for dilute astrophysical plasmas, it breaks down. Or in other words, the mean free path of electrons is quite big, so that the heat fluxes cannot be ignored. Or as the blob is displaced, it will exchange heat with its surroundings. So the other thing to note is that a lot of astrophysical plasmas, in fact, most of them, are magnetized. So if you have a magnetized plasmas, electrons are doing this gyro motion. So their displacement perpendicular to the field lines is small, whereas along the field lines, they can travel large distances. So the transport in a plasma, heat and momentum transport, is extremely anisotropic. So people talk about conductivity along field lines. So this heat flux due to thermal conduction is essentially only along the field lines, along B hat. B hat is the magnetic field unit vector. Right, so this is sort of a cartoon Brownian motion picture of isotropic diffusion. Particles are moving around on isotropic random walk. But if you have a plasma, particles are diffusing only along some local magnetic field line. And if you plug in the numbers for the systems that I'm interested in, known as galaxy clusters, and I'll actually tell you about what galaxy clusters are briefly, then I get a mean free path which is 0.3 kiloparsecs. To set the scale, this is sort of only a factor of 100 small compared to the scales of interest. Okay, so the transport is important. The other thing that we can calculate is the ratio of the Larmor radius and the mean free path. And for the typical parameters that we are in, it's actually tiny. So that means that the deviation of particles across the field lines are tiny, but along field lines are large. So it's extremely anisotropic system. And we can actually calculate the mean free, we can calculate the diffusion coefficients for such a system, and it's just the mean free path times the, the velocity times the step size, from Brownian motion type arguments. And it's just mean free path times the thermal velocity. So the diffusion coefficient along the field lines is much, many orders of magnitude bigger compared to the perpendicular diffusion. So essentially you just you ignore perpendicular diffusion and say all transport is anisotropic transport. So here is the astrophysical system that we are interested in. So galaxy clusters are the largest gravitationally relaxed systems in the universe. So here is a snapshot from a large cosmological simulations which shows the development of structure in the universe. So what you see, so the structure in the universe on the largest scales is in this form. So all this is driven by self-gravity. So if you start with very uniform initial conditions, gravity is inherently unstable. If a certain region is denser than its surroundings, it has a tendency to pull more and more matter. So it runs away. It's a gravitational instability which leads to this large-scale structure which has filaments, and at the intersection of these filaments you have things called halos. Okay, so galaxy clusters. So this is from an N-body simulation, very simple simulation which only has gravitational interaction between particles. So this gives you a correct large-scale picture of what is probably going on. But inside these this big halo is where we have galaxy clusters. So galaxy clusters are the largest or the most massive virialized structures in the universe. So this is just dark matter particles. But if we look at them using our X-ray telescopes, so we see this. So they emit profusely in X-rays. So this is a Chandra X-ray image of a nearby cluster. The same thing if we look in optical, basically the galaxies, we see this. So galaxy clusters observationally are just an overdensity of galaxies. So here, if you look at the mass picture, the dark matter picture, you have an overabundance of galaxies or mass in this region. So you can sort of map this region onto this. But this is actual observations. This is simulations. Okay? Right. So what they solve here is the gravitational N-body problem. So you have particles which interact by gm over r square, and you just let it go with the proper cosmological background. Yeah, with some smoothing, and there are a lot of techniques that are used for numerical reasons, but yeah, it's just Newton's law between all the particles. Yeah. Right. So by particle, I actually mean, it's dark matter particle, but it's like particle in cell simulations. When people simulate plasmas, they do not simulate a single electron and a proton. They simulate a cloud, an ensemble of many, many particles. No, nothing. It's just gravity. So it's actually simple, at least conceptually. Right. So I think for this talk, it's really not important to know what dark matter is. All you need to know is dark matter provides gravity. G comes from dark matter. Okay? So, and that's sort of just the motivation here. So once you have G, the baryons, which is normal matter, and it's subdominant. So you must have heard that most of the matter in the universe is dark matter, which is this. But there is also normal matter, and normal matter is sort of sitting in the gravity provided by dark matter. So this is actually the good picture to know. For example, Earth's atmosphere is sitting in the gravity provided by the Earth. So you can ignore the gravity of fluid elements in Earth's atmosphere. So you just take that picture and forget about what actually is responsible for that gravity. Okay, right. So let's the next. Right. So as I said, the nature of buoyancy or free convection in such plasmas is very, very different. So here I'm actually showing a very cartoon picture. It's actually very similar to the Schwarzschild convection cartoon that I showed earlier. So imagine gravity pointing in this direction and temperature which is increasing in this direction too. So it's and assume it to be stably stratified according to the classical adiabatic criterion. But keep in mind that it's extremely conductive plasma along field lines. So these black solid lines are field lines. So let's assume that in equilibrium, these two yellow blobs are at the same height. Now you perturb this magnetic field lines and these blobs, so this is frozen in, the plasma is frozen in with magnetic fields. So, I think one of the previous speakers pointed out about flux freezing. So, so now this perturbed blob and this perturbed blob are at different heights, but they are connected by magnetic fields, and the conductivity is very, very large. Because of that, this is no longer adiabatic. What this satisfies is it's at the same temperature. The magnetic field lines has the same temperature. The perturbed field line has the same temperature because conduction is extremely efficient along field lines. Okay? So this blob has the same temperature as this height. Okay? And of course, this is all done slowly, like in the standard convection case, that it's all subsonic. So you can assume pressure equilibrium at the same height. So this blob is at the same pressure as this new height, but its temperature is the same as this height. Okay? So temperature increases towards the bottom. So this blob, which is the same temperature as this height, is hotter than the background at that height, right? Because temperature gradient in the background points in this direction. So this is hotter than the background, and it's in pressure equilibrium. So the density is, rho times T is constant at that height. So this is this is hotter and lighter. So this is unstable, right? So this sort of an arrangement has a tendency to run away. Okay, and we can actually do a formal linear stability analysis and show that this is a robust linear instability in the WKB regime. That's correct. Right. That's right. So this guy will be heavier, so it will also, the system will be in a runaway situation. Right. Right. So basically what it says is if dt dz is negative, then it's unstable, even if the entropy gradient is stable according to the standard criteria. We have to keep in mind that we are in this regime, that the conduction time is much shorter compared to the sort of a buoyancy time scale, which is square root of h by g, where h is some sort of a scale height, which is actually okay for these systems. These are dilute conductive plasmas. So, this is essentially driven by anisotropic thermal conduction. This actually is very, very simple. It's even simpler than the standard Schwarzschild convection because here it's the temperature and rho times T is constant. So it actually doesn't even require any calculation. And this is actually a simple movie of this. These are initial field lines. So what this shows is field lines. So initially field lines are horizontal, and the vertical boundary conditions here are reflective. So the field lines, because it's an unstable equilibrium, have a tendency to become vertical. The blobs rising up and falling down sort of comb it in the vertical direction. But here you cannot get perfect vertical direction because of the boundary conditions. So people have tried different boundary conditions and sort of there is a tendency to comb the magnetic field lines like in the vertical direction. Right, so these are the equations, the standard equations, the mass conservation, momentum, induction equation, and the entropy equation, the energy equation. But keep in mind that we have anisotropic conduction, and this actually is what is responsible for changing the nature of buoyancy in these systems. The other thing is, there are two effects of magnetic fields in this problem. One is this J cross B force, or the magnetic tension. Right? If you have magnetic fields, they resist anything which sort of perturbs them, right? Because there is a magnetic tension force. The other is through this transport, anisotropic transport of heat. So what I'm actually focusing on much more is this transport part. And this is sort of the standard linear analysis, WKB analysis setup. You have gravity in the minus z hat direction and a magnetic field, a general magnetic field. So you can choose your coordinate system so that B is in the XZ plane. So it's sort of a regular magnetic field. And then the background is in hydrostatic equilibrium. And the standard WKB expansion. If you plug all this in, you get a dispersion relation which looks like this. So this is the geometry. Gravity pointing in minus z hat, B is in the XZ plane, and K can be in arbitrary direction. So this is the dispersion relation that you obtain. And so omega cond is the conductive response. So if you make conduction 0, so these terms go away. So you see that you have standard internal gravity waves. But if conduction is fast, that is omega cond going to infinity, these two terms are what balance each other. And that's what gives rise to these instabilities that I referred to. This is the dispersion relation in the appropriate fast conduction, small magnetic tension limit. So you have G d log T dz instead of G d log S dz, or entropy gradient. So it's driven by temperature gradients and not by entropy gradients, because a displaced fluid element doesn't conserve its entropy. It conserves its connections with the field lines. So other interesting thing to notice here is that there can be an instability for any direction or any sign of dt dz, as long as you're allowed to choose the magnetic field direction. So if your dt dz is negative, you can choose bz to be 0, and you have a negative sign of omega square. So omega is the oscillation frequency. If omega square is negative, you have an instability. On the other hand, if your dt dz is positive, you can choose bz to be 1. That is, you can have initial field lines which are vertical. That's also unstable. So this is a snapshot from the simulations of this other instability, which happens if your temperature gradient is positive. Okay? Temperature increases with height. So you have initial field lines which are vertical, and sort of the instability has a tendency to comb out the magnetic fields in the horizontal direction. And this is how this looks non-linearly. So these are actually robust linear instabilities, and it's pretty well established. This is a typical temperature profile collected from a bunch of clusters observationally. And you see that clusters have two regions. In the inner regions, temperature increases with height. In outer regions, temperature decreases with height. So these regions are prone to this second instability, or the heat-flux driven buoyancy instability, which has a tendency to make field lines horizontal. The outer regions are prone to the MTI, which has a tendency to make field lines vertical. Right. Now, all that is sort of linear WKB, but what happens if you go to a nonlinear regime? And that's actually quite interesting. So these are snapshots. Yes, yes. Right. What he's saying is some observations of galaxies show field lines to be spiral. But what I'm talking about is that even larger scales, these are halo scale field lines. So what I'm actually saying is, even if it is, large scale, any structure, I'm actually looking at a tiny box. And for that box, the local field lines can be taken, in some direction. Now, what is the implication of this? So this is a vertical field lines. Temperature increases with height. So this is temperature. So high temperature at top, low temperature at bottom, vertical field lines. This is unstable. So you can see the instability developing. And eventually, after many, many buoyancy times, it sort of combs it in the horizontal direction. Now this state only has waves. I mean, it essentially is like a stably stratified fluid in a classical sense. Because if you see, now in this stage, if you have horizontal field lines and if you perturb this blob, you'll see that there is a restoring force which brings it back to its original location. So the nonlinear saturated state of this instability is akin to a stably stratified atmosphere. Okay, and for mixing in a stably stratified atmosphere, we can define something called a turbulent Richardson number. So the physical setup is quite simple. You have a stably stratified box and you have some turbulence. Okay, you need some strength of turbulence in order to overcome the stable buoyancy response. So you can actually define a Richardson number, except that a turbulent Richardson number, because we are actually imagining some sort of turbulence in these intracluster medium, in the plasma that I'm talking about. And it has to work against this stratification, except that there is no d log S dr. There is d log T dr. So it's the temperature gradient which governs all this. And the temperature gradients are much shallower than the entropy gradients in clusters. So even small velocities can mix the intracluster medium well. So it's actually similar to the Mani's talk in the morning about the top layer of the ocean being sort of very weakly stratified. And that's why I had this immediately like, must be winds. So it's a similar thing that this is very weakly stratified. So anything else which is going on there can mix it up. Now here is an example of mixing in such a situation. So forget about all the details. What I'm showing is mixing of passive scalars, okay? So the bottom panel is adiabatic simulation. So what I have is some sort of a fan at the center, okay? Which is driving, it's sort of mixing in a small region within 10 kiloparsec, okay? And I have three kinds of setups. One is fully adiabatic, no conduction. This is with isotropic conduction, so full isotropic conduction, irrespective of magnetic field direction. This is anisotropic conduction only along field lines. And what you see is that the effect of mixing is much more with conduction than without conduction. And it's sort of expected, because if it is strongly stratified, external turbulence must be much higher if the stable buoyancy response is strong. And so anisotropic conduction is somewhere in the middle of adiabatic and isotropic conduction. And the reason is simple. There is a d log T dr here, which is smaller than d log S dr, but nonetheless, there is some sort of a restoring force. Whereas in perfect isotropic conduction, there is no restoring force. It's neutrally stable. Right, so I said that the nonlinear saturated state of HBI is like stably stratified flow. But that doesn't appear to be the case for the other instability, which combs the magnetic field in the vertical direction. So here is a simulation, snapshots from a simulation of the MTI. So initially horizontal field lines, temperature is maximum at the bottom. The magnetic field lines are combed in the vertical direction because of the instability. But in this case, even when it's sort of, the magnetic field lines become vertical and the linear instability stops, if you have horizontal flows, you can regenerate horizontal field lines because there is no buoyancy penalty in moving at the same height. In the previous case, when you're moving, you had to move in the vertical direction and there was a penalty because of buoyancy. Here, there is no. So it's much more isotropic. It doesn't just saturate by becoming vertical because flow can just move horizontally without any penalty. So I'm actually at the end of my talk. So these are actually very, very simple instabilities, and these have been around for a decade now. And people have looked at various aspects of it. These are more, it's actually very, very difficult to confirm these from observations, right? It's, all you have is X-ray photons. So, but they are, the physics-wise, they have very, very important implications, and I think the most important one is this mixing properties of the intracluster medium. So if you have conduction versus non-conducting plasma, the mixing properties are quite different. So even a small turbulent velocity coming from jets or mergers can give rise to widespread mixing of metals. We can observe the metals in the galaxy clusters, and the metals are very fairly well mixed. Can it be that this sort of conduction enables efficient mixing in galaxy clusters? There's a whole sort of set of Pandora's box waiting to be opened. There are a lot, since when your mean free path is the system size, a lot of plasma physics issues open up, and there are instabilities, and so it sort of becomes like the solar wind. There's a lot of interesting small-scale physics. It also has to do, it also has implications for dynamos in the intracluster medium. How does the intracluster medium generate magnetic fields? And a lot, I just sort of concentrated on galaxy clusters, but such dilute astrophysical plasmas are very common, even in accretion disks, accretion flows, and in sort of the solar corona is also dilute and anisotropically conducting. In fact, I'm actually done. I'll actually show that snapshot from the solar corona. Sun is fabulous. You can, this is the image of the sun in soft X-rays, and what you see are these loops. And what these loops show is essentially plasma density, because denser material emit much more efficiently. So you can actually, without any equations, just by eye, see that these are extremely anisotropic. You have these loops which sort of follow magnetic field lines. So even without any equations or anything, I can show this, and you will be convinced that this is an extremely anisotropic plasma. So I'll actually end with this. Thank you.
Thank you, Prateek, for very interesting talk, and we'll have time for 1 and 2 questions.
Sir?
To 0th order, yes. In detail, no, because there are substructures. So there is a big cluster and there are smaller clusters. So locally, you can have gravity pointing somewhere else. But on large scale, if you smooth over these scales, it's okay to assume centrally pointing gravity. Right. So, dilute basically means that conduction is important, right? So dilute means that mean free path is big, so that the perturbed blob is isothermal rather than adiabatic.
So first you say that the mean free path is big, and I have seen that you are using Navier-Stokes equation. So how does it conform with the general idea of continuum mechanics? That's the first thing. And the second thing is that what are the implications of these buoyancy-driven mixing? Are these hotspots for some formation of stars, or what implication?
Right. So the first question is that if the mean free path is comparable to the scales of interest, the whole sort of fluid picture breaks down, because Knudsen number is no longer small and all that. Right. So formally, what you're saying is absolutely right. For galaxy clusters, the mean free path is actually smaller than the system size. I said it was 0.3 kpc, whereas the system size is 100 kpc. But still, we have to worry. There are systems where the mean free path is bigger than the system size, like the solar wind. And yet, solar wind is, MHD equations describe the solar wind beautifully. And the reason for that is magnetic fields provide an effective collisionality to the plasma, so that, in some hand-wavy way, it actually works very nicely. So the tendency of magnetic particles to gyrate around magnetic fields prevent them from moving away from them. But along field lines, they can just be running very, very fast. But that sort of helps. This one.
Yeah.
This one?
Yeah, Bz square equals.
Right. So Bz is the unit vector, the Z component of unit vector. Right. So if I am given a dt dz, I can always choose my Bz. There may be some regions where magnetic field is vertical, horizontal, So if my dt dz is negative, let me go to the next slide. So this is the dispersion relation in the limit that I'm interested in. So if my dt dz is negative, and if my bz is 0, this is omega square is negative. So I have an instability. If my dt dz is positive, and if I choose my bz to be vertical, field line to be vertical, I again have an instability. So what I'm trying to say is, irrespective of your temperature gradient, if you're allowed to choose magnetic field directions, you have an instability. Oh, right. So here, right. So if you take the fast conduction limit, right, the slow conduction limit of this equation gives you, delta rho is n square delta v, So basically in the fast conduction limit, you set the left-hand side to 0. What you have is del dot delta q equal to 0, which essentially means that magnetic field lines are isothermal. Okay, so that the cartoon that I showed is actually fairly physically accurate, at least for this setup.
So these are basically non-boostless, no? You don't have divergence U is 0.
Right. So this is actually Boussinesque in the sense that we don't have sound waves here. Somewhere like an elastic, or you do have density gradients and so on. But this is WKB2, so KH for all scale heights H for density, pressure, entropy. The scale height is much bigger than inverse of K is. So this actually, you can do the full thing with sound waves. So if you do the full dispersion analysis without filtering out the sound waves, you get everything. You get slow, fast, the whole thing. In addition to these, but the beauty of Boussinesque is that you get what you're interested in less effort. Right. So if you look at the dispersion relation, this is very similar to internal gravity waves. It's the direction of K which is more important than the absolute value of K. So all modes grow at the same rate. So it picks out the mode where you have an initial perturbation. If your initial seed has a perturbation of certain scale, that will grow the fastest. But non-linearly, it will be different.
So any more question? If not, let's thank to Prateek once again.